here. This matrix is the Jacobian determinant. This is the Jacobian determinant. Jacobian determinant of x1 until xn, but xi is missing. We do not have xi because after xi minus 1 we have xi plus 1, so we do not have xi. So this determinant is the Jacobian determinant of x1, xi minus 1, xi plus 1 until xn, which is respect to u1, u2, un minus 1. Okay, so using our notation, we obtained that is to say ni is minus 1i plus 1, determinant of x1, xi minus 1, then xi plus 1, xn to the u1, un minus 1. Okay, so this is the result. But we use a useful notation to simplify this result. This can also be written as minus 1 I plus 1 x1. We learn xi, xn, then u1, un minus 1. But the xi is actually missing. Okay, in our result we do not have xi. But to indicate that xi is missing, we add a hat for xi. Okay, we add a hat for xi. This hat means missing. Means we do not have this term. Okay, so this is the final result of ni. So every ni we have obtained, and as you can see, when I is n, the nn is exactly our previous assumption here. Okay, so our this assumption is consistent with our final result. The expression for nn also included in our general expression for the coordinate of n. Okay, so our n is our vector, normal vector n is when n1 is when I equal to 1, n equal to 1, I equal to 1, I plus 1 is 2, minus 1 square is 1. So we have no sign here, but x2, xn to the u1, un minus 1. Then when I equal to 2, I plus 1 is 3, minus 1, 3 is minus. Then here we have x1, but we do not have x2, so x3, xn, and u1, un minus 1. Eventually, when I equal to n, we have n plus 1, x1, xn minus 1 over u1, un minus 1. So this is the final formula for computing the n minus 1 dimensional parametric surface in Rn, the normal vector of such a surface. Recall that in 3-dimensional, if n is 3, then x1, x2, x3 we denote by by x, y, z, and u1, u2 we denote by uv. Okay, so this formula becomes the x2, x3, that is yz, and uv, and the minus x1, x3, we do not have x2, that is xz, and uv. Finally, xy, uv. But this is precisely the second coordinate of this vector is precisely zx uv. Okay, you switch x and z means switch the two column of the Jacobian determinant. So the Jacobian determinant reverse its sign. Okay, so we see that when n equal to 3, our this general result becomes our previous result deduced from using the cross product of a three-dimensional space. Okay, so this is our method of computing the normal vector for surface, even in very high dimensional. Okay, in this reasoning, we see that linear algebra solving linear system of linear equations, the technique of solving system of linear equations are very useful in our solving this geometric problem. Okay. Now we go to our next chapter, inverse function theorem. Inverse function theorem and implicit function theorem. Okay. Firstly, we study the inverse function theorem. Before discuss the theorem itself, we make some preparation. Firstly, we have this algebraic result from linear algebra. Maybe no, because it involves the norm of vectors. Anyway, suppose A is an n by n matrix, square matrix. Then A immutable if and only if there is a constant C positive such that AH, the norm of AH is not less than C multiply the norm of H for any H in Rn. Okay, this is a very simple result involving the norm of vectors in Euclidean space. I will not prove this result here because the proof is quite easy, and you can consult the textbook. Okay. Now, because A is an metric, it can be considered as a linear map. A can be considered as a map, still denoted by A, Rn to Rn. AH, this map, a vector in Rn, say H is mapped to the multiplication of AH. So A is a map. This map is linear. Therefore, using the proposition, we see that if A is invertible, then for any x, y in Rn, we have ax minus ay, x minus y. This is quite easy because ax minus ay is precisely ax minus y. Then we apply the proposition which h is x minus y. We obtain the result. Okay, obtain the result in red. Okay, so this is algebra. So such a property is useful. A map which such a property is useful. We call this stable. So we have a definition. Suppose U is an open subset of Rn, and F is a map from U to Rn. We said this is stable. We said this map is stable when it is stable, if it satisfies this condition. If there is a constant C positive such that for any x, y in U, fx minus fy will not less than the norm of x minus y. If this inequality is true for some constant, say, and all xy in U, we say that the map F is stable. So this means if A is an invertible matrix, then considering A as a map from Rn to Rn, then the invertible matrix A as a map is stable. Okay. So this is the meaning of this definition is quite clear, and but we will not use this concept. Okay. But because this is a part of the textbook, I have to say something about it. Now, to prove the inverse function theorem, we need some preparation. Our next one is the very useful lemma about the continuity. Previously, for a metric A, we had defined the norm of the metric to be maximum of AX. Okay, and now if the metric A depends on X, it is not a constant matrix. A is dependent on X. That is, all the entries of the metric are function of X. X in some open set. So the norm of the matrix also depend on X. Therefore, we obtain a function. The value of this function at the point X in U is the norm of the matrix AX. So the property of this function we denoted by psi. This function is interesting. Is this a continuous function? This is a basic problem. And in the proof of the inverse function theorem, we need this function. So our next result will be concerned about this topic. And also, I will remind you that the norm of a metric has this satisfies the triangle inequality as well. We know triangle inequality for the norm of vectors, but it is also true for norm of matrix. That is to say, A plus B. Two matrices, the sum of the norm of the sum will not greater than the sum of their norm. Okay. The proof is very easy. I will show you. To prove this inequality, for any H in Rn with norm 1, the norm of A plus B H, this is the norm of AH plus BH, will not greater than the norm of AH plus the norm of BH, triangle inequality for vectors. But because the norm of H is 1, so the norm of AH will not greater than the norm of A. Okay, by the definition of the metric norm. Similarly, the norm of BH will not greater than the metric norm of B. And this inequality is true for every H on the unit sphere. That is, the norm of H is 1. So you take the maximum. You forget the intermediate part of the inequality. You only consider the first and the last result. And then you take the maximum. The maximum of this must also be not greater than the norm of the sum of the norm of A and the norm of B. But the maximum here is precisely the norm of A plus B. So this proves our inequality important in our argument later. Okay.